Sorry for that. Okay. So, well, actually, we're going to into the real thing now, so we are okay. Sorry for that. Okay, so let's try to break down that script. That I don't know why I say script, like that code, into something that we can manage a little bit without Arduino IDE. So this is the pinout again. This is PV0. This is the pin that we are trying to blink the LED on. As I said earlier, we have port A and port B. We have 14 pins, and we group them in bytes because it's an 8-bit or 1-byte architecture of microcontroller, and we can only have a maximum of bytes in the register set, and we understand that in a second. This is the memory map or the structure of the microcontroller. Not very important at the moment, but it has 16 kilobytes of flash, not that big. And here at the beginning, you see that it says 64 IO registers that are what we're gonna start talking about now. So what are the registers? And here, please correct me because probably my explanation is gonna be a little bit not accurate, but we could imagine the registers, and this is taken by from the microcontroller's summary, as a set of these deep switches, okay? That represent the status of things in the microcontroller. Those things can be, for instance, the pins. The status of the pin if, for instance, they are high or low. That can be if the pin is an output or an input. Or it could be if in an output, the bit is set to as high or as low. And for each of these things, we have a register that indicates this status.
Other way to put it a little bit more, I don't know, a bit simpler for my brain is the chip needs to remember his own state. And he's so stupid that he only has memory registers to remember it. If it's not in the memory, he doesn't know it. So if he has this input, this output as high, he needs to store it somewhere to know that output is on high. So you can access that register, memory registers to change the state of or to set the state. Because if you change something there, you will obey that. Because it's the only link to reality, let's say, to understand these states.
Yes. So we can understand them as somewhere that we store how things are or how we want things to be. And as a consequence, we can manage the status, for instance, of pins directly. What we're going to do is use only input-output registers today. And we're going to blink the LED using these registers. First of all, we're going to set whether or not the pin is an input or an output. And that has a register that normally is called dir or direction. That basically says if the if the pin is an input, it's a 0. If it's an output, it's a 1. So in that register, that in this case stores the status of port B, which is where we have our pin, our LED connected in the port B pin number 0. That pin is going to be set as 1 because we want it to be an output to be able to control the LED. So that's the direction register, okay? Here, port X means that port A, port B, port C, in case you have it, port D, depending on how many ports you have, because you have more pins, this will be grouped by 8, 8, 8, 8, and it will be A, B, C, D. In this particular case, in this microcontroller, the datasheet specifies that they are accessed in this way, port X.dir, but you will see that other architectures access or define the registers in a different way. For instance, dir A, dir B, or in many other things.
Well, the pins does not depend on
It's a lower level.
This, if we go into the, so that's the, well, that's I think the beauty of this. This is on, let me see, let me find this.
Exactly, when you say pin mode in Arduino, he's calling this to send the IT registers that what Arduino takes care if you compile it for another platform to get the program. So you only need to know which port pin mode, and then the Arduino takes care of translating that to the proper instruction depending on CPU.
And when did we tell Arduino to take care of that? When we selected in tools and we went into, if it does it, into board and selecting here. Here, behind that, when we do that, Arduino selects a set of definitions that are the conversion between what we write as an abstraction in the Arduino framework into the specifics of each microcontroller or each family of microcontrollers. Yeah, the people that develop these things, for instance, Mega Tiny Core, etc., they have to go to the datasheet and read the whole thing and convert the instructions from Arduino into what the microcontroller needs. Yeah.
Imagine to write code really low level for any board. You need to have a crazy memory to remember all the set of instructions for each of the boards. And you just want to do exactly the same. So it made sense to group all those right in one in a library and just abstract them with an instruction that makes sense for people.
And in this case, I think, well, at this moment, I get a little goosebumps somehow because you see the power of having an open project that does this for you and that does it and makes it in an affordable way into a lot of microcontrollers. And you see how this democratizes a little bit the idea of controlling the electronics and be able to program them yourself. Otherwise, this is 600 pages.
All the engineers normally are used to do that. If you want to program this chip, you need to read an encyclopedia about it and learn everything about it. And now you can jump a lot of the things that you need to learn for each chip because someone else does not. And I think one other thing to add about the goodness of open is, for example, ESP8266. You know that chip, right? The implementation of all this is not done by Arduino. It's done by a community. And that's why you have to link the page of the community inside the Arduino IDE. So he uses the work of someone else. So being an open project allows any community, any individual to provide the work for any chip that's out there. That's why it grows so fast. So,
yes? Yes, good. So here, how do I know that I have to access them that way? Because I read yesterday this part of the datasheet and basically tells me each port pin has a corresponding bit in the data direction register, port X dir, and data output value, port X out. Okay, so I know that we have 8-bit registers. And in this case, what I can do is just convert what I said earlier into the first step of our let's get out of Arduino abstraction life. And sorry. So in here, I'm gonna still keep the setup and the loop. But right now, what I'm going to do is set in the port B register that says what the direction of the pin is going to be. And this, imagine it as something like, if I take this, I see some weird faces. This is something like this. This is PV0. This is PV1. This is PV2. So on and so forth. If I put as 1 in here, I'm saying it's an output. If I put a 0, I'm saying it's an input, which is the same as doing pin mode 7 output.
So one note there, the cool thing about doing it that way is when you really need something the most efficient you want, in one instruction, you write all the pins, all the 4 pins, and set them as this. So if you use digital write, it has a little bit of overhead because it has to code some extra stuff each time he sets one pin. So when you want really the most efficient possible code because you're in the limit of your board, sometimes it's good to know this and substitute the digital write or whichever instruction algorithm provides to you to the low level of instruction.
Yeah. Plus, it reduces the size of your sketch or your code once it's compiled because it has less things to include into the.
It doesn't need the library. At the end, the thing.
It's quite smart.
We don't care about how many libraries we use, but the binary we produce is the one that's important. If the binary is the same, then perfect, we can use a library. So when libraries are well done, well, not well done, but it is possible to cover all the cases in the most efficient code. Sometimes you don't even know the difference, whether you code in a low level or with a library. Depending, you have to normally test. If you really want the most efficient, you test both functions. I have just only one space that with a encoder that I need to be updated really, really fast that I started to use access supports directly. But normally you don't have to, which is just good to know that it happens.
Yeah. So we set the direction of the port B. Here, honestly, I could have just said this is all ones. Doesn't really matter because I only want to know that the last one, the one that I want to use is an output. The register by default is gonna be like that. Actually, it's gonna be like this, but I just said it's an output and that's it. Now, as we read in here, the data output value is in this one here. So what I'm going to write now is port B out and the same. This is the pin PB0, PB1, PB2, PB3. And that's it because we don't have more than PB3. We only have 4 pins in port B, sorry. So it tells me registers to enable that pin as an output and to define the output state. And somewhere else, and this is like the normal convention, if I set that as a 1, it means that the pin is high. Remember that I've always said true or false, 1 or 0, high or low, 5 volts or 0, it's all the same at the end. So if I put this as 1, it's gonna be high. And then if I put it as 0, it's gonna be low. And still I'm using the delay. In here, we will remove it later as well, but I'm waiting between both of them.
One comment around the 2 instructions that we replaced. One disadvantage of doing it like this instead of the digital write is we are overwriting all the pins. So if the pins are being used for something else, the other pins, we are setting them as low right now. Okay. So normally digital write instruction takes care of reading the actual state, the current state, and just modifying the one that you want to modify and set it as they were before. And here we are not. We are just overwriting all the pins to 0, and the only one that we care, setting it to 1. Okay.
In this case, we will, don't worry, because we will work on that, and we will improve it in a second. And we will define our own digital write. But at the moment, Victor is right, we're writing all the ports, and we're just making this one. For now, we don't care because we only have one LED. But if we have many of them, we will be turning them all off and then all on. Of course, we wouldn't do this, and I will give you the solution in a second. But for now, just understand that when we're writing the register like this, we are actually setting the status of the LED. And now we have 1 second, so that we actually realize that this is happening. I don't know, what do you want for it to be? What do you want me to set for the delay so that we see a difference?
500.
500? Thank you. 500. Okay, so I'm going to compile it. It's going to put it in the same folder, so I don't have to look for it again. So as long as I don't change this name, it's going to put it always in the same one. And I'm going to reconnect all the setup. Actually, I could leave it like this because I'm already giving power here. So I don't need to do anything else. It's compiled, so I connected. And now this is all the same. So let's see, I send this. Amazing. Because at least in my setup, I cannot send it from the Arduino ID for these type of boards, okay? But I don't know if you see a change. I think it went much fast. It went halfway faster, but I'm just gonna change it and be a little more aggressive so that we actually see a change. Compiling, compile, send. Ta-ta-ta. And we both agree, we all agree that the LED changed, so I'm not telling you bullshit, I'm not lying to you. You can also see that from home, okay? So this works, that's a good news. That's good news. So what is the next step? As Victor was saying, we have some problems here with the ports. But before going into that, actually, let's remove all the setup and all the void loop and all these things. And I hope that you agree with me that if I take this and I substitute this by a while one, that's a loop, right? It's an endless loop. And I'm just gonna copy it over. So I have a while one. I have the same instructions. And here I also forgot about the delay from Arduino, the delay function, but I had to include something from the AVR utils called delay. It's another header file that includes just that part, not the whole Arduino framework, just the delay and the input output. Okay. Actually, I don't think I need this. Let's check. This one here, this is in here because first of all, I had to read a little bit in the datasheet, but I'm gonna show you actually what happens if I don't put that. That basically tells the microcontroller, it's a flag for the microcontroller at which speed it has to run or which clock speed is set at. The microcontroller doesn't know that in many cases by default. So you have to tell it, you are using this clock scaling, which means this number 33333 corresponds to 20 megahertz of clock speed. If you don't put that, you'll see that the microcontroller doesn't understand the time well, and it goes faster or slower. And in this case, we'll see that it goes slow. The rest is the same. This is just a function. It's called main, has a while loop inside. This is the equivalent to our setup, and this is the equivalent to our loop. So basically, it's all the same. I'm gonna compile it, and we're gonna set it to 1 second. We'll see that it will be much longer than 1 second. And I'm gonna send it. So it's been sent, and you see, the microcontroller now thinks that the time is going much slower than it actually is. This is because we didn't define that the clock speed that we use in the microcontroller is not the same as the execution one.
This microcontroller uses a crystal?
No, but it has a register for the CPU speed. That is.
So he has a counter. You have to tell how much time passed between each time he counts. If he doesn't know it, maybe he get it wrong. Every time he thinks it's a second, in fact, 5 seconds.
It's 5 seconds.
You can choose different values.
Yeah, but normally if you use the default clock or internal clock that it has, it's going to be 20 megahertz. If you put an external one, the same one as this one, for instance, that might be different speed, faster normally, because you want to improve the capabilities or the speed that it can run at, you have to set that to a different thing.
Yeah, and you can also do those over and say power. It's what we do with laptops. We take down the speed of the CPU or take it out depending on how much power we are on battery or not.
Exactly. So I'm gonna compile this. Now the only thing that I changed is this value. It gave me a warning because it was already defined somewhere else, but don't worry, it's okay. And now I'm gonna send it and we're gonna see that this is actually going to be a second again. That's a second again, okay? So that instruction there is necessary. And here we almost solved all our problems except the one that we were mentioning earlier that we're writing the whole register every time. But here already we don't have any.
Arduino doesn't exist.
Arduino doesn't exist, exactly. And here we have 200 bytes of sketch. 1% of program storage space. Let's see how much it took earlier. Let's do this. 200 bytes, remember? Let's have a look at how much it changes, if it actually changes anything. 790. It's 4 times lower. Yeah.
And it's not always in this proportion, depending on which instruction you're using. It's very difficult to really get how much you are going to save doing it. And when you have a very long code and you want to optimize it, don't do it just because you think it will be reduced at a part, not necessarily. Yeah. So sometimes it's good to do a research and say, okay, if I change this, maybe I can save a lot. But this instruction is very well optimized in Arduino, so it doesn't work the case to change it. Okay.
Yeah, but we already see that this has a lot of potential, especially it allows us to understand very detailed things or low-level things. Now let's go to the next step, which is we're gonna start manipulating the bits inside the registers in a very specific way. And for this, we have to understand what is called bit manipulation. So it's a way that we have to manipulate, let's say, array of bits in a way that we can move things around and make displacement of bits or cancellation of bits or setting bits to 1 or 0 in a specific location. First instruction is called bit shifting, which is basically we want to turn something that is like 0, 0, 0, 0, 0, 0, 0, all zeros, into something that is 0, 0, 0, 1, 0, 0, 0. How can we do that? So basically I could say something like, I want to take 1, a value that is just this, and I want to move it 1, 2, 3, 4 spots, okay? So how do I do this? I take this value 1 and I move it to the left 4 spots. And that is gonna give me, sorry, I'll put it in here. That gives me that. Okay, actually 1, 2, 3, 4, yeah. If I want to just move it, no?
No, sorry. I'm just checking. Normally it's good to have a calculator.
Actually,
show you the value in bits. So you can always easily just click the bits and get the number.
So actually, let's do that. So let's take, I think if I do this, 1 shifted 4. Actually, I made one mistake. Is actually
more.
No, it's fine. Yeah,
it's fine.
Yeah, it's fine. So I moved 1 4 times, and now I have 16, which is the binary for that.
Equal that value to 16, and it will be the same. Okay, you're just changing from the decimal to hexadecimal to binary to whatever you want, but the value is the same.
Yeah. if I want to, for instance, just put a 1 in here, which is what we need. Sorry, I take this one and I want to put a 1 in here, and I just want to do that. How many numbers should I go? 0. So
0.
Exactly. So if I take 1.0 equal, I have a 1 there magically. Okay. So now let's do that in our port register.
Can you please show again how you did it in the calculator?
Yes. So if you, I'm using Mac, but if you go into the calculator by default, you have to set it as programmer. And then in here, you will view all these operations on the left, and 2's complement and 1 complement. Don't worry about that on the right, but on the left, you also have these parts, and you have to set it as decimal. So in here, if I click on 1, then X, so bit shifting to the left, I press that, and then I press 4, equal. Okay.
Thanks.
And in the small numbers, 0s and 1s, where the bits are shown, you can check that.
Exactly.
The right thing. No?
In here, you exactly get that thing. And here up there, you have the decimal conversion. And you can change this into X, dec, or octal. Okay. So that's the first one, bit shifting. Now imagine that we want to do, we just want to change 1 bit in a specific location. And for that, we're gonna do what we call bit masking. So bit masking has different options, but imagine that we want to do something like, we want to have something like this, and we want to convert it to something like this. Okay, so we have a 1 here, and we want to convert it into a 0 here. Or we want to do the opposite. So we want to do this, and then we want, and then we want to get this. So for this, we have to go back a little bit to high school and remember logic gates and or gates and things like this. And remember that the AND operation is always 0 except when both inputs are 1. So if I have input 1, input 2, and output, I have 0, 0, 0, 0, 1, 0, 1, 0, 0, and 1, 1, 1. Okay, that's an AND. If I do the same for the OR, it changes a little bit, and it doesn't matter whether or not one or the other is 1, but we have 1 here and 1 here. Okay, so how can we do this first one? Let's say I want your help here. How can I, what do I have to do for converting this into this? Anyone can help me?
Say again, please, Oscar.
Yes, so you see line, I want to convert this into this.
And with 0.
I'm sorry?
And with 0.
I have to and with 0, that's correct. Yeah. And if I do 0, 0, 1, da, 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 and I do 0, 0, all zeros, and I do an AND operation, 0, 0, stays the same, 0, da, 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 I get to here, 0, 1, 0, the rest 0, 0, 0. So I converted this into this, okay? What happens if I want to do the opposite? I want to convert line 21, well now 22, into line 24. What do I have to do? Or, exactly. Exactly. So I want, so is 1, 1, 1, 1, 1, 1 in the position of the 1. Perfect. So I have this, and I do an OR operation. So I do OR 0, 0, 0. This goes into 1, 0, 0, 0, 0, 0. Okay? So basically we did OR, and here we did AND. Okay?
So with an AND, you can remove bits, or you can add bits easily to an already.
No idea what that means.
Yeah, sorry. Let me just put it like this. So that is the result. And this is the result, okay? Yeah, do we all agree on this? Do we all see this or not? Please don't be shy.
Not really.
Okay, but so let's start over. We want to convert this this line in here. Do you see the screen? Okay, the line 15.
Yeah, if you say the number, it might be better because it's hard to see the cursor.
Yeah, it's line 15, and I want to convert it into line 18. Okay, and what I'm doing is what we call bitwise operation, which is I'm taking one byte, one by one, and comparing it to something else. And I'm doing an operation one by one. So if I want to convert this byte, sorry, this bit here, the bit in line 15 in the 6th position into a 0, what can I do? What kind of logic operation could I apply to that bit to convert it into a 0? Following these tables in here. So I want to take a 1 and I want to apply something to convert it into a 0. So in this table, I take and I see that inputs that I have, 0 doesn't work, 0 doesn't work, 1, okay, this one might work. This one here, no, but the output is a 1. I want to convert it into a 0. The same here, input is 1, and no matter what I put is a 1, so it doesn't work that way. Take an AND with a 0, and it gives me a 0. So if I do an AND, let me put it this way this time.
Okay.
0, 0, 0, 0, 0, 0. That will give me this, right? Because these two ones give me these two zeros, sorry, give me a 0. These next ones the same. And here I say and 1 and 0, 0. Okay?
But how are those two operations defined, the and the or? So technically,
it's here. You see the table? So, so here I have input 1 and input 2, and here the output. And I know that my inputs are only zeros or ones. So I make the combination, and I define the output that can only be 1 when both of them are 1, and the rest of the situations are 0. And for or is not the opposite, but is a little bit less strict, meaning that no matter which one of the inputs is 1 or true, that the output is going to be true.
Okay.
Remember that when you compare 2 bytes to arrays of 8 bits, it compares 1 by 1 depending on the position.
Exactly. Exactly. So that's why this is called bitwise operation, because it does it bit by bit. Okay. Okay. So that's there. And we already know how to move bits. So bit shifting and bit masking. Okay.
Why do we use AND, OR, and logic gates? I think you already talked about transistors and logic gates. Very easy to build 2 transistors and AND gates. So try to think about that this is happening inside the black box, inside the silicon. So it's just a couple of transistors to make that operation. Because in our logic, we will make that byte 0 equals 0. No, we have to think in the tools we have inside the microcontroller. And 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 OR are very simple rules that we already have there for no cost, let's say, for a couple of transistors. That's why we use this kind of operation. That's normally we don't use it.
Exactly. So let's try to convert all this into actual code. And for this, we're gonna go into what are our requirements, which is I have port b.dir. Okay, that is 0, 0, 0, 0, 0, 0, 0, 0 per default. And I want to convert that into this, okay? Number one. Second thing that I want to do is port b.out. I want to start from start end. I want to start in that situation. And since I want to turn my LED on, I want to do this. But I don't want to write all of this, as we were talking about. I only want to modify this one, okay? Then, after a certain delay, I want to do the opposite. And I want to turn a 1 into a 0. And then I want to wait again.
The zeros, just on the shift operation shift 7.
Yeah.
And it feels, when there's no value, it feels it with 0.
Exactly. So let's give it a try, okay? So how could we do this first one? We have port b.dir, and I want to do what? Which at the beginning is like this, okay? So we want to do 1 shifted 0. Yeah, okay, that works for me. But one thing, well, let's leave it like that. Then this one here. Port b out equal 1 shifted by 0.
And what happened with the rest of the bits? Do we modify them or not?
Yes, we do.
Remember, we should write all the numbers. So if there were other ones around, we are up to moving them. So all lengths are going to change, no? If we have a set of 8 lengths connected.
Yeah, and actually here we might be changing the status of some other pins, even if they were set as outputs, because they would be to 1, and now we change them to 0. Okay, so what can we do here? We use an operation, okay. And what operations do you think we should use? We want to turn something as a 0 into a 1. And we have a 1 in the position that we want. So we are in the inputs. Here, this doesn't work. Because
The OR, no?
The OR, right? Okay. And here, I have a 1 and I have a 0. Okay, so I'm gonna do an OR operation. This signifies OR. And that's it.
Or equal. That means he's using the previous value.
12 hours.
Applying an OR on top of it. No? So even if we have a value that's not 0, 0, 0, 0, we're going to get the previous value and adding a 1 at the end or at the beginning.
And correct me if I'm wrong, but this should be the same as this. Yeah. So just to be clear, it's the same as I don't know if you've done this at some point, but is if you have a variable that is a or value equal 0, and then I want to increment it, you could do value equal value plus 2, or you could do value plus equal 2.
That's the same. No?
This is equivalent.
See, coding, those two sentences mean exactly the same. So that's why he's taking the previous value on port B dot zero and just adding the bit that she shifted to the first place, 0, and ORing it with the previous value.
So it will remain the same. You see that in OR, basically our input remains the same unless we put a 1 in it, right? So 0 stays at 0, 1 stays at 1, 1 stays at 1. Except if you put a 1, which is what we put in here. Yeah?
I see places that, no. So at the end, what he's doing is he's reading the value that's already there in the chip. That's port B dot in, okay? And he's saying, I want to apply the OR operation on top of that original state of just ORing 0, 0, 0, 0, 0, 0, 0, 1. The value that we want. Just setting to 1 the first bit on the chain. When you apply an OR operation to those two chains, to arrays, you get what you want. You don't know what's happening with the first 7, the last 7 bits, but you know that you are changing the first one to 1. The rest, if they were 1, they will remain 1. And if they were 0, they will remain 0. Yeah, because an OR operation with a 0 doesn't modify the original value, right? If you have a 1, you will have a 1, you OR it with 0, and if you have a 0 and OR it with 0, you still have a 0. You don't modify it. Yeah?
Yeah.
If you need to set another thing out after this, you need to OR it.
If you want to set 2 different pins, you can OR it once with the both values set to 1. Because he's shifting the value, but you can also OR it with a set of pins right in my hand, let's say. No?
You said like shifting 2 pins. How do you do that? Like you put 1, comma
1, the arrow, instead of a 0, you put a 2. Well,
yeah,
one.
If you want to shift 2 pins, like everything is 0, you want
and you have to do it twice.
Or with 1 shift twice.
Exactly.
Or with 1 shift 0. Okay.
Exactly. OR it with zeros and only the ones you want will always give you ones in the position you're injecting, and the rest will be respected. So you can OR on top of the value as many times as you want to add different ones to the chain.
Yeah.
We should build a tool to play with this, because if we make a small game where you can just do like space invaders with bits,
yeah,
I'm sure we will get it at this.
Okay, so do you agree with me that I could do the same with the port B out? Exactly the same. So I'm just gonna do that one. Okay, here I'm just setting the last bit the same way as I did in here. Okay. Should we try the last one? This is gonna be a little bit more complex, but it's gonna work as well. Before we do that, I have a question. Because right now I have the feeling that either you are not interested in this or that you think it's too complex, and I want to know which one it is. If it's you're not interested, we can just stop wasting our time and we can just skip it. You read it at home and we go home, and I'd rather grab a beer in the sun and rather than being here. If you think if it's too complex, but still you want to listen to it, we can still dedicate our time. But if you don't care about it, because I see that you are not even looking at the screen sometimes, that's okay. So please tell us. I'm being totally honest, and it's not a critic.
Yeah, it's not a problem.
It's not a problem, but if, I mean, at the end I have a to-do list that if I showed you to you, and he has another one that is 20 million lines. So.
But also, if you're interested, we are totally willing to re-explain it again.
And we can stay here till 3 p.m.
Yes.
But please make use of it. Yes.
I have like one point of view coming from someone who doesn't know programming. I'm understanding what we're doing right now, but I'm not quite capturing how to use that on a practical, I don't know if I'm saying myself. So technically, I'm not even sure if this is something that we're doing to change the command that we're giving to one pin or to the full microcontroller, and how can I implement that in order to do what? I know it sounds like I understand the math of it if you want, but I don't really get how to use it.
So the idea, at least how I see it, is that, so this week, and as you know this, that FAL Academy, we try to atomize every single process into different weeks, and especially in the electronics. The whole purpose is that you understand the core concepts so that you can be creative. Of course, we can do just Arduino classes, and we could spend hours doing this here. But at the end, you can do that everywhere in any tutorial that you find online, and it will come with practice. The point of this is that we understand how these things are done, so that if in case we need them, probably we're not going to use them. At least this week, you have to use them. You have to program your boards in as many ways as possible. So using Arduino, using things like this, like C, etc., etc. But in general, you might not use them, but still they are useful. And you'll see, especially in networking and some other weeks, when you start making more complex things, that these things will come back at hand and will simplify your life. Now, at least as I see, is that we try to give you all of this because this is not, let's say, a standard course for Arduino. We're talking about electronics, and it's more powerful from my point of view to learn these basics, even if they sound very alien and complicated at the beginning, so that you can have all that mindset ready there for when you have to use it, and little by little practice and understand it. That's my point of view. If you want to add anything.
No, I totally agree. I think that the important part, I know that some of these things are really boring and sometimes complex, and we don't find the meaning of them. But we try not to teach recipes. Yeah, you can bring a leg just connecting this board and uploading the example. Yeah, but that doesn't give you the potential to develop anything by yourself. No? So we think that these kind of things are important to understand the foundations. No? And how do you use this? Trying to respond to the question. We can try to re-explain it a little bit, but at the end, this is what is happening on the chip level. So if you learn how to write the full register of the port A and port B, and learn how to add or remove bits from that register, you can change the pin mode and digital write and digital read for instructions that will be a lot faster, a lot smaller. So that the main advantage is you can get a binary that's a lot smaller and that runs a lot faster. And also, you understand when you're writing digital write what you are really doing. You are just shifting a bit in the port B set of bits and writing the state register of the microcontroller. So maybe it's not that important that today you go out from here doing bit math like a master, but just to understand the concept that you have some sections of memory inside the microcontroller that tells the microcontroller his state and what to do. And you can access them directly and write on top of them. Okay? So imagine that in your brain you have some switches, and if I just switch this one, your arm will do this. And if I ask you, where is your arm? You just have to check that switch and say, hey, my arm is off. Okay? So that's it. The only thing is, this is at the end so simple that we just have a couple of arrays of 8 zeros and 1, 8 zeros and 1 to manage in or out, and to manage voltage or ground. It's just, at the end, it's just that.
Yeah.
I hope that clarifies a little bit.
And also, or one concept that I think it's important to talk about is this particular case is super simple, and it's so simple that it's intentionally simple so that we can see all these concepts. But one day, and not very far from now, you're going to have to build a machine. That machine will have motors, will have Actuators like will probably heat up an extruder. If you have a 3D printer, will have to move things, axes, etc. When you use that, you'll at some points probably just use libraries and you'll just use some things. But if you want to make something more complex or that you want to customize, imagine that you just want to add an LED into that. There are many ways to just do it, but knowing certain type of basics at some point will come at hand. And you will see that the guy that created the library said that there's a register that you can set and that does something, and that something turns on the spindle, for instance. And you know, oh, registers. That I remember from the LED stupid class. Or maybe if I just manipulate that register and I put a 1 in there, it works. Oh, the spindle is on. Or I don't know. But these type of things, at some point, bear with me because they will come handy, especially when you build your own things. Right now, this is a very toy example, but at some point you'll see, oh, the register for the interrupt, whatever, or oh, something that I want to do that is not working, Oscar. Remember that at some point in the future, and not so long from now, because the machines are coming, these things will be somewhere. Yeah.
And at the end, I think the important part is to understand the concepts of you interact with chips, writing and reading registers, memory. So for example, I have faced a lot of times interacting with sensors, external digital sensors that you interact via I2C. That doesn't matter. But at the end, you only do exactly the same. You just send instructions to write these bits into one, and you check the data sheet and know that that bit means that you will receive centigrade Fahrenheit or whatever type of metric. And then you just read these 3 bits and you get the value. And at the end, it's just that. Interacting between chips is just writing and read registers.
It's really powerful. I think probably we're overextending into this. Let's keep going. But I think it's really, these concepts are really, really powerful. Let's keep going. Right now, we were in the last one. Let's do this one and let's try to do it a little quicker. So how can we do this conversion from 1 to 0 in there? We needed maybe AND, someone said. So port B out equal maybe the same as before, 1, 0, and what else?
Why 1, 0? Because we already have 1, 0 on the...
Oh, well, sorry, okay, know that, okay. I got ahead. What should we do here? If I want to convert this into this, I'm gonna do the operation on port B out.
And it's 0. And port B out.
Okay, and so, and.
No, more. Sorry.
And that's all. I have not.
You just do an AND with a 0.
Yeah.
With a complete 0.
Zero. And
okay. But if I put everything 0,
then the OR is the port B out.
I do, sorry, explain me again. So what do I put in here?
So
this is all zeros?
And the port B out is that. On 0. Then the OR, closing.
To port B out.
Yeah, but then we will get back the 1.
But the thing is, we already changed port B out to be a 0. So we are already with,
and here
that's already 0, right?
When we do that, it changes the whole thing.
So we're applying the operation directly.
Okay.
yeah. So what do you think? Maybe if we put a 1 in here, what does it do?
Mm-hmm.
This is not going to work yet.
Yeah.
But what happens here?
Because we put everything to all the other, we impact all the other ones.
And what if
you do the opposite?
If this means no, so this is
This is negative.
This is equal to that. If I do this, let's simplify it a little bit. I do AND with this, and meaning if I put a 1 in here, no matter what I get in the input, sorry, I have I had a 1 in here. If I had a 0, I get a 0. If I had a 1, I have a 1. So I don't touch it. Whatever I got, I respect everything, right? But in here, I put a 0. And if I put a 0, I convert into a 0 no matter what you give me. So you give me a 1, I put a 0. You give me a 0, I keep a 0. So that's what we want, right? So we want to negate this and then AND it. If I convert this into this, do you agree that is the same?
Yes.
And if I convert this into this, do you agree that is the same?
Yeah, just a question, please. When we go to the AND operation, technically you said if you give a 0, I mean, if you give a 0 or a 1, it gives a 0. Yeah, it does. Sorry, yeah.
40 and 41, right?
Any of the inputs being 0, guarantee you a 0 as an output.
Like to keep the bit, you can either lower it to 0 or end it with 1.
Exactly.
Yeah.
Exactly. Depending if you want to add a bit or remove a bit. So that's the two basics. To write some bit respecting the rest, or to unset that bit respecting the rest.
Yeah.
And keep in mind that sometimes it works the case to spend some time getting it right and as simple as possible, because sometimes you do this, I don't know, 1 million times a second. And if you have to do 2 operations to do the same thing instead of 1, you double the time of execution of real time. So sometimes if these are tiny important operations, it works the case to do it.
Yeah. So I'm gonna modify this. We were doing this before. Now I'm gonna do this. Okay. It looks more cryptic, but we understand what we're doing, right? Each step might look a little bit more like what, but there it is. So I didn't need that one. I'm gonna
impress your friends.
Yeah. It doesn't work if you want to date a girl. It would have to be a very weird girl. I don't know, Lynn, do you like this? No, right? Anyway, so I sent this. Well, actually, I didn't change the delay. Let's change it. I see the LED here. I'm gonna just put in this. I compile it, and then compile.
And it's so small that we are not going to see nothing.
10.
It's just a fade outlet.
It's very quick here.
Yeah.
Let's put it
for my eyes.
Yeah, maybe with one of your iPhones, you could improve this. If I send it, boom. Okay, so it's working. We're getting.
How much space do we use?
216. So it's a little
same as before.
It's almost the same, but we are adding some extra things in here, but we are not writing all the registers, so we're not modifying the whole set of pins. Okay.
So this will work respecting the rest of the pins and managing overlaps or whatever we want. And the size is almost 8 times less than the normal version, but the same that we did.
It's 16 bytes more, because it only probably these operations in here. Yeah. Now, this is, if we have to write each of them, it becomes a little bit complex. So we can do the same as Arduino does with what we call macros. Macros, and you will see this in many scripts or many examples that basically are defined with hashtag or ampersand, pound define. What does that mean? It means that if I say, as the one in here, if I say define pin LED equal 0, sorry, like that, define pin LED 0, it means that before we flash it, the compiler is gonna take everywhere that we put pin LED on the script and it's going to replace that with a 0. It's as if we had a variable, but it's changed in compiling time, not in runtime.
It's even before compiling time. In fact, no, that's why it's called preprocessor. No, what I'm trying to say is you can use this. Imagine that you write a program and you give it to your friend, so it replaces all the operations of that, and then you compile. So at the end, the compiler doesn't know whatever happened before. It's just kind of macros, no? It's like having an assistant that will replace all your shortcuts with the big thing by hand, one by one. Okay.
What is the difference between this and this? If I did this in here, it would work the same way in practical terms. But here we have one variable that we are not changing. We could probably do this as well, but we are not changing that variable. It's only just for us, for understanding the script and maybe be able at some point to change that and put a 9. But it's not gonna take a space in the memory that we use when we run the script in the microcontroller. And this happens in your computer. Imagine that you are using, like, I don't know, Photoshop, Illustrator, Blender, Fusion, everything, and you see that your computer is getting slow, right? And at some point, probably something comes up and says, your computer is running out of memory. You say, but my hard drive is full. No, but it's not the hard drive memory, it's the RAM memory, which is where your computer stores the variables, let's say, in a very simple way for the analogy. But your computer at some point will keep those variables somewhere in memory, in the RAM, and the microcontroller does the same. And it does it with stack, the stack memory, which is where it keeps the memory, the variables in the memory, and it does it in a dynamic way, etc. That's where it comes, then it's stack overflow name, which basically you overflow the stack and you don't have enough space to keep all your variables. How can we reduce that? If we have a variable that we're not going to change, we just can define it. And we're not going to take space for that variable in runtime in the stack for the microcontroller. We're just going to have it flashed. It means that we're going to use the space of the memory dedicated to write the code. And it's not even going to be a variable. It's just going to have the name, the actual value that we put in here. And as he was saying, we do that before even we call GCC. So we do that, and it's doing just a preprocessor, which is basically as if I did a command, find and replace, and did pin LED, I put a 9 everywhere. It does it the same way as you would do in any other text program, let's say. Find and replace, the same. We can do that with values, or we can do that with functions. And here it becomes the powerful thing. We can define macros that do these operations for us, and that we can put friendly names, for instance, pin mode, set, clear, digital write, digital read, etc. Okay? So more or less.
This last one, because this function has to be done during runtime, not during the preprocessing.
Yeah, but we are
in fact what the preprocessing, what it's doing is just substitute the text on your file with the same operation, copying the same operation a lot of times, and you just use a simple word that defines that operation. But it's happening before compile time. The compiler will receive the code as we wrote it at the beginning, repeating all the long operations by hand. Okay, so in fact, in terms of size and compiling, it's the same, but it's a lot easier for us to write code if we just use whatever mnemonic or a small thing for a long function.
Yeah, So let's try to define those things. I have the cheat sheet in here, but let's try to do this first operation as a macro. So we're going to convert this into a macro. I will do the first one, and then we'll try to work on the other two. Macros can also receive somewhat variables that are not actually variables, but that get understood by the preprocessor as things that we can substitute. What does that mean? Let's do this one. I'm going to define something like output. I want to set a pin as an output, and I want to define what pin. So I just do output pin. And then I'm going to say that whenever I find output pin, I'm going to put this. So I'm going to say pin and port, sorry. So I'm going to say port or equal. I'm just copying what I have above. 1, then pin. And whenever I say output pin number 0, port B. Actually, I should do port B, then it will replace all that. Actually, this has to be like that. And we'll set this as an output. Okay?
Remember that he is just, not Oscar, but the preprocessor, he's just replacing words, not doing any complex operation, just copy paste words. No?
Yeah. So if I take pin is equal 0, I put it in here, 0. Port B, port is equal port, so put it here. Do you agree with me that what I get there is the same as in here? So we do that pre-processing, and now we have that already defined, and I don't have to call this complex thing that I was calling before like this, but I can just call output pin port.
So this pin mode of Arduino, is it a library or is it?
It's a library because he has to deal with different architectures. And here we just made a macro that only deals with this kind of chips. Okay?
Yeah.
But sometimes you can even, in your code, put, if this is the chip, use or my own macro. But if this is not that chip, if we are compiling for another chip, use the Arduino implementation, so we don't have to deal with it. So you can optimize code just for this processor, without struggling with the rest, let's say.
Yep. Okay, so let's do the rest. Let's do this one here. We want here to say an instruction, for instance, that we're going to call set. And it will set the pin high. Okay? Only for high right now. How do we do this? What do we need?
You understand the syntax of the define. You put the word define, then the word that will appear on the code, space, and then the replacement that you want to be substituting the first word. Okay? So you can't use spaces in your first thing, I think. No?
Yeah. Word to find. Something like that. And then space, word, replace. Yeah. That's how it works. And there's a space here, and there's a space here. So here, actually, this would be like that. Okay? Because this space here could be understood as the replacement already. So let's do this one. Set pin and port. And then
I think you can use the spaces in the definition.
I'm not sure either, but we can try. So port dot out, and then the same, right? Pin and a 1. Yeah. Let's do clear. In this case, clear, same pin dot and port. And here we go port.out, and we just take this, right? Put it in here, and I replace the 0 with a pin. So all of a sudden, we have 3 macros that are somehow like functions, but are not functions, are pseudo, well, are macros actually, that will be replaced and will do the same operation, pre-processing. And we will see if this changes or not the size of our sketch. So let's give it a try. C is the same. Set and clear, the delay. We had 216 before. I'm gonna remove this one that is not necessary. And here it has spaces, it's okay, but not in here. Here, I'm not sure. I'm not sure, let's try. No, I didn't like it. Oh, in definition of clear. No, that's okay. Left sheet of negative value. Oh. Okay. And actually, let's do this already. Define pin pin LED 0. So I have pin LED, pin LED, pin LED. So I have this up here, and then this there. So I compile. $2,216. So we didn't change the size at all. The preprocessor did it for us. And if I flash this, we have 1 second, and this is at 100. So I send it, and let's see if this works. It does, right? The delay changed. Okay.
So in this class, Oscar is so fast and intelligent that he replaced all the Arduino library work with a most efficient one in half an hour.
And yeah, so that's the same, actually, I think. Yeah, it's the same. Okay, so you're telling me that Arduino is doing all that for us, digital read, digital write, etc. Registers, value equal low, what we did, negation and an AND, value equal high or equal in the bit on the port register. Has more complexity, but you can already see these registers. And I'm not making this up. This is Arduino. And this is Arduino Core AVR, wiring digital. And up here you have the definitions of both things. So Arduino is doing this for us, and I think it's quite beautiful that we already rewrote that in 2-3 hours. Of course, we don't rewrite the whole thing, but there it is. Next step. Do we want to take a break? Yeah, let's take a break and be here at quarter to 1, 10 minutes, if you agree. Sorry? So we're gonna talk a little bit about the tool chain and how we can make a make file. That is, let's say, a set of instructions for our computer to do what Arduino does when we click verify and upload, what we do it ourselves. And then I'll try to do that in maybe 15 minutes, just skim through and refer you to the documentation so that Victor has time from 1 to 2.
I think half an hour is more than enough for platform. But
oh, okay. No, but still, I think that we already give you like a lot of info. So probably let's try to make this part a little fast, let's say not too deep. And then go into Platform IO, which you'll see that we will make our life easier a little bit again. It doesn't mean that we have to do this as we did it today, But again, basics gives you a lot of power. Okay, let's be here in 10 minutes.
Bon,
c'est trop compliqué.
Ah, non, j'aime bien. Et je ne vais pas rajouter un truc dessus, mais dans mon travail, il faut que je lise les MDN, ce type de fichier, c'est tout en binaire. Et chaque fois que j'arrive là, c'est trop compliqué, j'arrête. C'est important de voir les chiffres, les opérations chiffres, tout ça, j'avais jamais vu.
Ça, il faut essayer un petit peu quand même. Pratiquer avec Sublime ou quelque chose. Tu mets là, tu fais le code, tout ça. Sinon, ça va être possible.
Parce que là, c'est très orienté au processeur. Moi, quand je le fais sur des fichiers dédiés, c'est encore un autre domaine, mais
c'est facile, mettre là dans l'autre domaine. Okay. Let's wait for the rest. If you want, do you have any doubts that you feel comfortable asking? Any questions?
I have a question. I understand the logics and what we are doing, but I'm not really comfortable with that. For example, usually we're having like, you have to put space here because it's not going to understand it. Is there like any kind of form? Like when I get to this command, this what you did that, it's a /// is state. Again, what we did with the defines and all that stuff is inside any documentation of C or C++. And if you check the C++ preprocessor, people find documentation exactly how to manage, which is the syntax. So all of those are based on standard. And in this case, it's C or C++. In this case, it's called preprocessor. I don't know the word. If you search for preprocessor points in C, you will find it. Yeah, it's something in fact that is not for Arduino or for embedded programming. It's support from the standard C.
What should they design Python
No. No.
Processor from Python to what they understand.
Not that I know. I mean, Python.
So the limitation is the process compiling. If you have a program which would convert Python to what
it's more complex than that. So of course, yeah, if someone creates a processor or even a preprocessor that converts your Python code into C code, or a compiler that can interpret the Python code and convert it to ADR compatible code, let's say, then you're good to go. But it's not that simple because normally these kind of processors are designed with a language already defined. The architecture or the instruction set of the ADR, they provide code to build it based on a specific language.
So, because I use the ESP32, so the
fact, it's more complex. Python is an interpreted language. I think that's the correct word.
Yeah.
So what they do is they run an interpreter in C inside the chip. So when he receives Python code, he understands how to translate that inside the chip to an instruction.
It's actually flashed like here.
You flash a MicroPython.
Okay.
It's a core, a C writing core that understands Python languages, a subset of Python, not all the Python things, and executes them inside the chip. So it's like if you are running Python in your computer, you're running Python there.
So if I'm using, because I want to try that, I want MicroPython to try.
Normally, MicroPython has a very high requirements in terms of RAM. You need a microcontroller that has a lot of RAM to run MicroPython.
ESP32, you can.
Yeah, that's
And
yeah.
You can do that, yeah.
Because I did not see the whole flashing.
You can do that, but I can refer you to, I don't know MicroPython, but I can refer you to Benjamin documentation. Is actually that guy.
The hairy one. Okay.
This guy last year played a lot with MicroPython. This is his documentation. And I'm not asking that you refer to him, but if you want to check, he documented everything pretty well. So using the same ESP32, and I recommend that you check what he did if you want to run the instructions. There's some funny videos even.
Just a parenthesis there. I think I don't know if you agree, we insist that you learn the low level and the C stuff, because if you only learn how to program in Python, you depend completely on someone developing a proper interpreter and implemented the thing that you want to do.
So that's one of my questions for the assignment. Then it's better to work with the Arduino and C.
Yeah. And if you learn that, for example, sometimes people use ESP32 with Python and wants to access the E2S bus, and a specific bus for high-speed audio data. And no one has implemented that in MicroPython, so you cannot use it. Okay? No. As far as I know, I don't know, no one has succeeded on that. Maybe if you have the MicroPython code, then you can run some C, but I haven't seen that. Maybe it's possible. I'm sure it's possible. I haven't seen it.
Because I got somebody in the C, and then I wanted to try MicroPython. So you have studying the process.
Yeah, the microPython is the interpreter.
In this week, what I recommend that you do is that you try as many things as possible, and that you mainly explore things. It's not going to be a week in which you are going to learn programming. That will take years. And sorry, but it's the way it is. There's no immediacy in that. But this week is that you try how to use the Arduino IDE and flash your board with the Arduino IDE and you set it up. Then you use another editor and you use the command line. You use MicroPython if you want instead of C++. That you use, for instance, for the ESP, you can use the ESP framework that they already provide for flashing this. And some people last year and in the academy, they tried as well. Here we give you the core, which at the end is C, which is what is the foundation for all the rest that everyone else has built on top. Meaning that if you wanted to do your own Arduino core or Arduino scripts without having to use Arduino or ESP, SPIF, SPIF is called? ESP framework, ¿cómo se llama? Expressive, yeah. That's the framework for, it's like a framework for ESPs, same as Arduino, but like different. You can also do that one, or you can use MicroPython, but at the end, you will find one that you like. And then you will try probably at the beginning Arduino IDE, and in some years you will use Platform IO with the command line, or you will use whatever, but you have all those tools there. Yeah. The idea this week is that for me, if you keep it simple and you read a button and blink a LED with many different ways possible, is more valuable than if you make a super complex setup with sensors, motors, and things like this. You will have time to do that. Okay? This week is to explore, okay? And to make your computer work with everything, try to find different setups, etc. Okay?
At the end, keep in mind that the Arduino framework is a good thing for the middle point. So you don't need to be a assembler or writing code in 1 to 0, but you have access to almost everything. Python is a lot higher level, so you have a more simple, let's say, with more conceptual access to everything. But since the distance between that and what we call the bare metal, that directly acts on the chip, is so big, there's a lot of steps that if are not well done or don't exist, you cannot bypass them. So the Arduino language, let's say C, but with the Arduino framework, is like a good middle ground to. So my opinion is it's worth the case to learn to use C and C++ in this case.
Yeah. Answering the question from you, if you just look for preprocessor directives, C++, there's the C++.com is just one of the million references that there is out there. Preprocessor directives, it gives you not very nice website, sorry, but it
is nice. It's 90s.
Now it's retro. It's retro. Okay, now let's talk about toolchain. This I don't want to talk too much, but it's basically repeating what we were talking about before earlier. What is the process between converting our .ino file into something that we send to the microcontroller, and who is in charge of each step? So in this case, my internet is very slow, but that process is taken care of by a series of tools that depend on the type of microcontroller that we're using. For instance, we're using an AVR series microcontroller. Jesus Christ. Just to see an image, you have to just do this. That since we're using an AVR microcontroller, then almost all of them are going to start by AVR ta 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 ta. First one is the compiler, GCC, that takes the source file and converts it into an initial object file. Then it links other libraries in a process called linking. That is, if we have a look in here, compiling, and then down somewhere it says linking everything together. So first we compile different things, then we link it, and we put everything from the system libraries and the Arduino code into a same file. Then we convert that into X file using object copy. And finally, someone called AVR dudes uploads the X file using the protocol or the communication that we have, either serial or whatever else, into the microcontroller, okay? So that's more or less the different steps. Now, we could do this, all this process by hitting a button in Arduino IDE saying verify, and it does up until X, or upload, and it uploads the thing into the microcontroller. That's what you know how to do already, and there's millions of tutorials on how to do that. Now, what if we wanted to make something similar, but ourselves, okay? So that's where it comes, what we call the make file. And that basically is gonna take the series of instructions that we define for each of these steps, and we're gonna put it into a recipe that we can call from the command line. This is a convenient method that is developed mainly for this purpose, and that is as simple as just creating a file that has instructions, and that we save that file somewhere where we want to go into where we have our scripts that our Arduino file or our C++ file, etc. somewhere, and we just call that make file. Okay. Here, of course, there's syntax and things like that, but basically just understand this as a set of instructions that have a name called make file. That's the convention. Okay. Then if I go here and I go to, where is this? Where am I? I'm just gonna put it in desktop. And I go to my desktop. I will just call make. And it will read the make file that I just have created. And it will execute the instructions that I defined in there. Those set of instructions can be anything. Actually, it doesn't have to even be for compiling things. It can be for anything that you like. Just make, and you can even pass it arguments, and it could do, it could act accordingly depending on the things that you set. But we're gonna use it for the purpose of compiling and flashing things. So let's do one example. First is, or let's bring down each of these steps. First thing that we do, sorry, I had to change to another microcontroller here because I couldn't use the same one as in here, but it all applies. First, we compile the code and we use AVR GCC. And this is gonna be our first instruction. We compile it for our one target. Don't worry about these flags, but basically we want to take one input file called whatever.c, whatever.cpp, whatever.ino, and convert it into something that is called .out, which is this first thing. Actually, we would do that. Actually, that one is gonna do this one too, I think, right? I'm not sure. The linking is here? Yeah. Okay. Then I want to take that output, this one, and convert it into an X file. The command that I use is AVR object copy, and I take this input from before and I convert it into an X file. These are just commands. I don't want to go into detail of each of them, but basically it converts one to another. And then the last one checks the code size. Finally, if we want to program it, we use AVR-DUD, taking that hello file, and we flash it using a programmer, etc. Mm-hmm.
The step from the INO file to the C file? Yeah,
the INO file actually is the same. INO is a text file, so it's just.
So the first comment you can
yeah, no problem. What happens if I run all of this in my command line? This would work already. What I'm gonna show you is how we can put all that into file that does everything for us. And let me save this in somewhere that I have a blink. Projects. Actually, I will put it on the documentation as well. Sorry, too many folders, but I already have it in here. Assets, and we're gonna call this make file, just like that, okay? This is the convention. So there. Then I'm gonna also take Blink, that is my code, my script, which is gonna be the same as we used earlier, which is this one here, okay? And I'm gonna save that in my same folder, and I'm gonna call that hello.blink.44. And I'm gonna save that. And I missed, sorry. Let me just change that. I missed a C. Okay, this could be dots. This is, sorry, this is in this folder, and I have the make file, and I have the script. Okay, this could be called .ino, could be called anything. So I don't care. Exactly, the only thing that it has to match is what we put in here. Okay, this is basically, you can see this as find and replace, constant find and replace things into the make file. We define this variable project, which is the script that we want. And this variable project can be put into here. And this is the name of the file that I just created, .c. Okay, so if I take this in here, that's my file name. Why do I put it in here? Because I'm gonna be changing the extension into each of the operations. I'm gonna be calling it hello blink 44 out, X, etc., okay? Here I define what is my microcontroller. These are flags that I sent into the compiler. This is the CPU speed. These are flags that we defined on the AVR dude that are the same as the one that we have in here. 80 tiny, 1614, CPU speed, etc. Don't worry that much about what these actually are, but there are basically extensions that we put in the command that this will reproduce later. And then here I have basically a set of instructions that define what do I want to get, what do I need to get that, and what are the instructions that I need to execute to be able to get there. So I want to get first an out file from my source. What is my source? This one. So if I put this in here, I'm going to make that. I'm going to make a .out file from a .c file. And how am I going to make it? With AVR GCC. Just going to duplicate that. Taking this.
You don't need to do that. You're just doing that for training purposes.
Exactly.
You just leave it as it is because in the first line is defining variable with the content. The software already replaces those.
Exactly. I'm just doing it for demonstration, like for showing you, but it's not necessary, of course. And this command, if I build this command with all these variables, and let's do this first one just as an exercise, I can take MMCU 80 tiny 44. FCPU, this one. This command, I put it in my command line, and it complains because it's whatever, but in principle, it's executing this line in here, which is compiling the thing. Let me just take this one, actually. It's gonna be easier. This works for anywhere that has AVR GCC installed.
That means that you have to be in. So I think in Windows, you have to install. What do they need to install in Windows to be able to do this?
I'm not sure. I'm not sure, but in the academy guides, there's like, I think the person to talk would be Edu or Giuseppe, because they both use Windows. Yeah. But basically,
it's very difficult to maintain the knowledge for another system normally don't use. So that we don't spend enough time to learn how to do it in all of the classes.
Yeah. So let me rerun this. I just changed here. What happens? For the because okay, it's just that is for. Let me just change this. Here be.
This is different processor.
Yeah. Let me fix that 1 second.
First set of lines is creating the X file based on the out file. Though it's written from the C to make the out.
They're almost both, as you can see on top of the instructions, there was like a line defining what you have, what you obtain. And the first one means the one that the last line produces. So it is run in the order that's needed.
Okay, so whatever you think,
As far as I remember, is like that. And that's why you define, I need this, and I want this. Sorry, I at least I explain this.
Yeah.
Well, he starts from whatever he needs to start to get the proper order for the packets, because he knows that to obtain the X needs the out, and he finds another one that gives him the out. So it's that.
Yeah. So actually, yeah, if you see here, what we're trying.
And finds a way to solve the issue.
Basically, what we're saying is that in line 9, we are trying to get the X. For that, we need an out. We don't know where the out is because we don't have it in here, but it keeps it in here. So from that, we just need the source that we already know. Yeah, and we execute this, and this will not be, say, let's say, on a script as a variable or something. It will create the file in the disk, and it will save it in there, and it will call it whatever.out. And then this one will go here and take .out and convert it into X, okay? Which is what we're doing now with the command line. So here, just to make sure I don't have anything in here that says, actually, let me make another folder. Make example. And I'm gonna move make file into make example. And then I'm gonna move the hello into the make example. Okay. So sorry, in here I only have the make file. I only have the make file and the C code, okay? So if I do the first instruction, that is this one, taking the C file and sending it into a .out file. No, it's the problem is not there. It's this one. I have missing semicolons. Okay. PA6 is undeclared, which is, let's say, I don't know, number 3. Doesn't matter now. What is happening? Warning, DDIR undeclared.
I think you have a mismatch. Which are you for who you are trying to compile?
Maybe you need to define the problem. First define.
No.
Maybe you need to define the constants before.
No, because
the thing is, those constants that he's complaining should be defined in the source of ADR library. I think the problem is that you have a mismatch between the names you're using and the chips that you define.
Get this one from here.
That's why we use tools to do it.
Exactly.
We don't do it by hand.
It's tiny. Should be okay. Tiny 44. Let's take this one. I don't know. It's for the purpose of showing. Let's see if this works.
The command you're using, does it has the proper chip define?
Principle, yeah. Let's make MCU.
But the command
no, yeah, exactly. The command that I'm doing, MMCU, yeah.
1614. That's a problem. I think that's what.
You're so smart.
Well, the thing is, in the makefile.
Sorry, just to make sure that we are understanding what we're doing. I'm running each of the instructions of the makefile first in the command line, and we will use later the makefile.
Right now, he's testing that what he puts inside the makefile is working. You normally don't do that, but he's doing it because he's giving a class, and he realized that the command he's executing has the wrong chip defined. So the defines that were in the code didn't exist for the chip he was asking.
Exactly. So here, the chip is 44. So now with all this, all good. And now I have one file that is out. Let's have a look at that file. We won't understand anything, but it's already a compiled version of this thing. But it's not the X file, but it's an intermediate object, okay? Let's see what happens. Now we have this out file here, and we need to get to the X. So for this one, I need to take the object that I created, the out object, and convert it into X. So if I do this and I make the command myself, can you just do that? And if I paste that in there, now I have an X file. If I check the X file, this is my code that I'm going to send into Arduino. Okay?
It's impressive that that set of numbers tells everything to the microcontroller.
Okay. And the last step would be to send it to the microcontroller, but I don't have the setup to do that. Now, let's do the same, but making use of the makefile so that we don't have to create these commands ourselves. That's the whole purpose of this recipe, okay? And with that I stop bothering you. So I have in here, I'm gonna remove the hello C X so that you don't think that I'm lying to you. And then I'm gonna remove the out. I don't have anything there, okay? I'm just gonna do make, missing separator. What's going on? Missing separator. Let's see. Let me recopy the original one because I might have made a mistake while modifying all these things. Let's see. Good. So make. It did the first instruction here, GCC. It ran this part, and it created the out file. And then it created the X file. And it also checked the size of our script telling us that it was using 100 bytes, text data input loader, and I don't know, the program and the variables, let's say, okay? And now we have both our X and out files that we're able to send again. If I had a microcontroller that I can flash, I could say make, and for instance, take this one or another programmer of the ones that we showed in the electronics programming week and say make this, and additionally, we'll find this command in here and we'll take avr_do and execute this part, which is what is sending the program into, or the X file into the chip. And before that, it will find the X file. It doesn't have it, so it creates it from here, but it needs an out file. It doesn't have it, it creates it from here. Yeah. So let's try to do that. It's not gonna work. It will repeat the same thing. But now you see that we call avr_do for that chip and say, could not find USB channel. Yeah, because I haven't connected it. But this could work event, like if I had this connected, okay?
And you can see that it's nice because you can define different targets in your makefile code. So you can define bootload to different chips, you can define the source code, you can define whichever set of commands you think that you arbitrary name. It's normal, for example, in C code, just have a make clean that will remove all the compiled code. Make whatever, make build, make.
Actually, we could do something like remove everything.out, remove everything.x, and that's it, no? If I do make, sorry, if I do this, ls, I have those two. If I do make clean, removing, bye. Okay. So you can see that it could be for anything else, but in this case, we are making a small command line tool that helps us programming much faster. So we could be writing our code in here, make, there it is, compiled. How much did that take? Nothing. How much does this take?
Yeah. And imagine the size of the computer you need to run a Java virtual machine that runs Arduino on top instead of just running make. You can run it on a Pi 0 and it has more than enough RAM and whatever.
Cheating.
Like this.
Okay.
Mac is still thinking on how to do it.
Yeah. So that's the power of this. Of course, again, not to do this week everything, but maybe try some of these things. If you find some make files for your chip that are pre-done, a lot of them are already in the documentation from Neil. If you want to have some, if you go to embedded programming, and with this I finish. Here you'll see where here all these boards and make. This is the make file for that board. Okay, and it has exactly the same. The project, the tiny device, the CPU, where do you flash it with, the baud rate. And here you see, actually I could have used this one because it flashes, sorry, it compiles and it makes the X file, then, sorry, it makes the out file, then the X file, and then uses PyUPDI with the same flags that we were doing manually into a make file. So you could use this one in case you have one of these things. Yeah, and it's exactly the same. Okay, actually we could try it. I'm not gonna do it, but because it's already 1:30 and he hasn't started. But at the end, if you go into the embedded programming and you look into make, a lot of them. Okay. Good.
I need a Zoom mic. share my screen out there.
No, puedes conectarte. ¿No tienes el invite del calendario? En el calendario tienes el evento. Do you guys have any question before he goes into?
In case our microcontroller does not have a name, can you start from the name and change some parameters?
Yeah. Yeah. In case you don't find any, as I did yesterday, I tried to compile a guide for you for all the types of microcontrollers that you have in the academy. And again, it's in classes and, microcontroller summary here. Just refer to this whenever you're lost and to each of the images when it loads. That will specify what do you have to do for each of them, where you compile, how you compile, if there are makefiles, not, etc., etc. Okay. You have for AVR, ARM, and ESP not here, and I will put it later. Yeah. In debugging mode, yeah, you can do that. You need some advanced tools. It's called EDBG. It's not an easy task, but basically, if you want to, for instance, stop the execution of the program and analyze what's going on as variables and things like this, you could do it. But basically, you have to tell the microcontroller to, guys, could you lower down a little? So you can send the code compiled with what we call flags, which basically are telling the microcontroller to understand certain points as checkpoints or important parts in which you can be stopped and in which you can halt for a second, and someone else could inspect what you have. So you have to compile with flags, and then you use a tool called EDBG for connecting to the microcontroller and talking to it and receive via serial communication what the status of the memory is, modify variables, etc. Not an easy thing. It's possible, and only people like Victor are able to do those things.
I don't remember anything. I have to follow my notes every time.
And it's not easy.
You need to do very often to keep it in your brain.
My advice is that if you're not going to be like high-end developer for Atmel, that you can just use serial print to print the status of variables. We will see that. We will do some sessions on debugging and understanding some problems when we have more complex setups. And one of those things is going to be that. Just do a serial print, and that's that.
Interested on that, we have built a guide for debugging the code with smart cities. That's something 21. So a lot of boards can be used with that same setup, and it's online. And we explain all the steps to arrive to a working.
Exactly. That is this guide that he's talking about. You can use it with a Pi. And there's instructions on how to do almost the whole setup and wire it and everything. And as you can see, there's a lot of things here to consider, but it's possible. A serial print is enough.
Serial print is more than enough. You can even write your own, for example, it's good practice to write your own macros, like preprocessor macros, like the ones Oscar example today, to do debugging. So you can have a flag at the top of your code, debug true or false. And you can have a macro that only when you turn on debugging will print a lot of outputs just to see that everything is working. And when you turn that off, your code will run normally. That's a middle point, let's say, between using a real debugger and using a serial port for debugging purposes. And there are already libraries to do that properly. For the ESP, for the Arduino, so you install a library and you set up just a couple of things to output information via the serial. For the ESP, you can do debugging via Wi-Fi also and stuff like that. Okay. And I just click share screen. Yeah. Or I'm not able to do it. Or yeah. Okay. Well, I'm not gonna spend too much time. The idea is just to explain a little bit what is Platform IO and how can we use it in a practical way. What it is almost the same that we have seen today with Arduino IDE or with a Makefile. It's a tool to build code and upload code to boards for embedded coding, but it has a set of tools that's very big. And I'm going to do a small review on what's there. So our conclusion is that it's powerful enough to do big projects with the hassle that is involved in using Arduino IDE or using a Makefile. Okay, it's like a point where you don't have to write your Makefile step by step, but you have a lot of control and a lot of tools to manage libraries, to manage flags and stuff like that. Okay. So how does it work? I'm going to do a simple example in a couple of minutes on how to do the hello world with a Platform IO. You have to install Platform IO in your computer to be able to use it. There are a lot of guides. In fact, in the official documentation, they explain how to do it in different platforms. I'm used to Linux, so I only do Pacman -S Platform IO, and I have it running. Okay. Platform IO has a lot of integration. For example, people use it inside VS Code, inside Atom, inside Git text editors. You can do that. I'm not going to explain nothing around that because I don't use it and I don't see the point. You can keep independent your tools to compile and upload code than your text editor. In that way, you are more versatile. You can use any text editor, the one you like, with the tools you like, and just use a couple of commands to upload your code. There's people that loves to have a button to do everything, so it's possible. Okay. One of the main advantages of Platform IO is that it takes care of for us on managing all the code that we are using from other people, meaning libraries, meaning frameworks, meaning whatever thing that we need to install to upload our code, because for now we have been using, or Oscar have been using ADRQ to upload code to ADR kits. But for the ESP, we need another tool, okay, to convert the code, to compile the code, and then to upload it to the board. And Platform IO, if we said to him, we're going to use this chip, he takes care of downloading all the needed tools to compile, to link, and to upload the code. And we don't have to do it by hand. And we don't even care if he's using ADR2 or ESP2. We only care about which chip we are programming. And he takes care of downloading all of that. In the example I'm going to make in a minute, I'm going to explain the different parts on the structure of the directory, the different configuration files, the boards, etc. Just as a big idea, the thing is you can use several configuration files to set up which board you're using. Board meaning not only the chip, but also the configuration of the board, okay? Because you can have an Atmega 328 in an Arduino Uno that has these pins exposed and these fuse settings, etc., or you can have the same chip in another board that only exposes 5 pins, okay? So there are configurations per board, and you can build your own. That's a good thing about Platform IO. It's very extensible. You can do your own stuff, and you can write scripts to do a lot of things. So you have control under the hood, let's say. But it comes with a lot of, for mainly all the normal boards, it comes with the definitions already there. There is Once you install Platform.io, you have a command that's Platform.io or PO for short, that has a lot of different parts, okay? Right now, I was talking about boards. Boards is, for instance, the first thing we need to take care of. No? Which board are we going to program? So if I do command PO boards, if you just do PO, he will tell you the different commands that exist, okay? I'm just gonna cover the basics, and if you are interested in this tool, you can later go on. And normally, I use it a lot, but I don't use, I just use a couple of commands normally, because I don't care about the terminal monitor. I use my own. You can use whichever terminal monitor you want. It's not mandatory to use this one. But if you do PO boards, boom, no, you have a list of a lot of boards, okay? So you can filter this output. You don't need to explore it by hand. But I just did that so you get the idea that a lot of boards are supported, okay? So for example, I want to program an ESP32 back there. So I do a PO boards and I write ESP32, okay? So there is not that many, but still a lot. You know? So if I have there is a name here, a long name. So for example, node MCU is a common one, no? So I'm sure around here, if I write node MCU, I have here the node MCU 1.0. That's normally the board that we use to program those cheap Chinese ESP82 boards. In the Arduino IDE, you can find exactly the same name, okay? And this is the code or the ID for that board. So we need to remember, if we want to program that board, we need to check in this list and remember this, okay, the ID. So for my example, I'm going to use a simple Arduino Uno. Okay, it's obviously supported in Platform.io, supported almost in whichever software you can find for programming boards. So if I search, for example, for Uno, there is too many, no? But one of these should be Uno, okay? At Mega 328 is the chip, this is the frequency, the size of the flash, the size of the RAM, and the normal name. That's my board, okay? If I check here, it's an Arduino Uno, everything matches, okay? So that's the board I'm gonna use, and I know that my ID is Uno. With that, I solved almost all of my troubles around installing tools, etc., etc. The good thing about this is when you install Arduino IDE, you have a lot of tools also, but they are already in your computer always. Platform.io will only download the tools you need for the boards you're working on. So it's a lot smaller and a lot faster normally, okay? So I'm gonna start doing a hands-on exercise, let's say. So I'm gonna do a hello world for this board, yeah?
So we need internet to run this.
You need internet the first time you compile for that board, because he will download the libraries. If you add a new library, you need internet, yeah. The same as in Arduino IDE, or you need to have the library locally, so you can copy locally, but yeah, you need access to the code from the libraries, the tools, etc.
If you have done it once, then
If you do it once and you don't add any new library, you should be safe for running offline, okay? So if you check the commands, there is a command, no, it's not defined here. Well, there is a command. I don't know where you can find in the documentation. I'm sure it is defined. That's PO init. Okay? PO init will start a new project for us. So it's the normal way to, I want to write a new code for this board. So I do a PO init. It will set up the folder structure with all the needed parts for us to have libraries, tools, whatever we need, okay? So I'm gonna make before a folder. Okay, so I'm going to keep everything in there. So I do a PO init, and now I can say -B to select a board already. I can change it later by hand, but if I do it here, he will set up the initial configuration file for that board, okay? So that's a good practice because it saves some time. So if you already identified which board you want to use, then you just know, you just have to put here the ID, okay? You do this, and he already built everything and gives a brief explanation on what's in there, okay? Include folder is to put your header files for including external things. The lib folder is to put your own libraries, not libraries that you're going to share with anyone, but well, from yourself that you're going to use just in this project. Source is to put the code. And this file, platform.io, is where you make the normal changes on which board you're using, which environment, etc. Okay, this is the file structure, and your code should be inside here. Okay. So first of all, I'm going to do it like this. Let's check platform.io init, and based on that, I'm going to explain a couple of more of concepts. If we see this file, well, as a parenthesis, you can use whichever text editor you like, okay? That's another good thing, because normally people that code has their own text editor set up as they like, with auto-completion, with whatever they like, and you don't have to use the Arduino IDE ugly text editor that doesn't have much tools, etc. You can write your code wherever you like and just go out to the terminal and execute a PO or whatever, and you're good to go, okay? Now, this file, the minimal of this file will define these three variables. The environment, in this case, is called uno. Depending on the type of board, you will find which environment you need to define. And well, in fact, this is a name that you define, sorry, I said it wrong. This is because you can write your code for several environments. For example, you can write a code that you intend to run in an ESP, but also in an AVR chip, okay? Obviously, you have to take that in mind when you write your code, that all the code is compatible with both platforms. But platform.io will take care of installing both of the things that are needed to compile for one environment and for the other. And when you compile, you just set platform.io, I want to compile it now and upload it to this environment, to the Uno. So he will download everything, compile for the Uno, and upload to a Uno board. And if you want to compile for the ESP, you just say environment Uno, sorry, ESP. And inside the environment, you define the three main variables for this project: the platform, the board, and the framework. Okay? I'm going to go back to the terminal, sorry, so you can see what those variables mean. If we execute PO, again, you can see here platform, okay? It has a platform manager. What is a platform? Let's try to understand. If I just do this, what did I do wrong? List, I think I need to use, yeah, to list the available platforms, no? So you can see here, Atmel AVR, and there's a description, and this platform is for all the Atmel products that use the AVR architecture, right? Atmel SAM is for all the Atmel chips that use the SAMD architecture. ESP is for all the chips that, okay? So you can use whichever platform platform.io supports, and it depends on the architecture of the chip. The next thing is the board. We already see the abilities to search for boards and all the settings around it. And then the framework. We have talked a lot about, well, Oscar has talked a lot about Arduino framework, no? But there's a lot of different frameworks to program for an AVR chip. We can check which ones are here. I think with framework. No, it's not like that, sorry. This is the kind of comments that normally I don't do because I don't change frameworks so often, but we can search for the help. It's package, I think, no? No, package is not. How do you list the frameworks? You remember, Oscar? No.
Let me check.
Like this, PO platform frameworks, okay? Because they are part of the platforms section, let's say. I'm just listing the ones for ABI right now, I think, okay? No, I'm wrong, I'm listing all of them. So Arduino framework, we already talked about it, no? Is the one that provides to you digital write, analog read, all those normal common pin mode, etc. We have different frameworks for ESP. You remember that we talked about Expressive some time ago. I'm sure there's around here something related to that one. There, here. SPDF, that's the ID name. Expressive IoT development framework. Okay, this is the most close to bare metal framework to work with ESPs. No, it's the one that the fabricator of the chip offers. Free R2 this free RTOS. Sorry, my English is not. This one is very nice, for example, for programming some D21 chips because it gives you kind of an OS features, no, of a timing, whatever. You don't have to work with delays with the way you will normally work in Arduino, etc. There's a lot of different frameworks. I'm not going to extend on explaining most of those, but as you can see, there's a lot of work done around the different frameworks. Normally, they are specific for a type of use. Arduino is one of the most versatile. And since the community is so big, you have a lot of extra stuff that maybe in some niche framework you won't have, okay? So for now, as students of Fab Academy, Arduino framework is more than enough to do whichever you need to do here. But just for you to know that there's a lot of things there, okay? Now, once we define this, Platform IO knows everything he needs to know to compile our code. So we can just write the code in a file and compile it. Later, after doing that, I'm going to show you the library manager. Okay, so if you remember, inside the source folder is where, maybe I make it bigger. It's, well, I'm the only blind guy here, right? I hope. So inside the source folder is where we put our code, right? So I'm going to make a file there called whatever, blink.ino, okay? So I create that file and I open that file for editing. No, this is not the one that I want, sorry. I don't know why I opened. I was in UnoFab. Okay, source. I put it in the wrong place. So let me put it here, right? Blink.ino, okay? So I need to write my normal code. Sorry. So let's just do a normal blink. digital rights, right? Sorry to make it to this. Now this is slow.
Sorry to make you see this.
Yeah, I shouldn't do it here, but okay. So I wrote that code that's ready to, if I didn't make any mistake, that should work in any Arduino, right? Everyone understands that code, etc. So now I'm in that folder. Here is my platform.io ini file that you already seen it. It's just these 3 lines defining my environment. And if I just do a PO to see the help, you can see around here, there's run project targets. Okay, you can build, you can upload, you can clean. Those words are very similar to the make file words that we normally use, right? Because obviously the guys that designed platform.io inherited all the practices from a make file. Okay, so this is kind of a make file on steroids with a lot of managers for libraries, platforms, etc. So now I already have, I'm sure, everything installed to compile for Arduino Uno, so you are not going to see the download part of it. But if I just do PO run, he will check if that everything is available. Here you can see configuration, whatever, which platform, etc. He's using framework Arduino ABR, toolchain Atmel ABR. All of those packages contain all the needed tools, compilers, whatever. He does exactly the same as before. He compiles. Here, everything creates the objects. The X file is here. Okay, so at the end is the same process that we already seen inside the Arduino IDE with a make file, but with another tool that does it for you. You can see that the speed of compilation was a lot faster than the Arduino IDE, very similar to the one used inside a make file. Huh? Yep.
I want to run your code, so I take your code, I put it here, and the platform that I create another environment.
You don't need to. You just copy my code and do PIO run.
But I don't have the same chip.
Ah, okay. So you just create another environment. You copy the same of me. You don't need to init a new project. You get my project and just in the platform.io ini add another environment. We can do that as an example now in a minute. I just want to do the upload part so you see everything. And before that, I'm sure that normally in your home folder, depending on your platform, Windows, Mac has it in different places. Platform.io does a hidden folder where he installs the libraries and the packages, etc. So I'm gonna, here in platforms, I'm gonna remove the Atmel ADR from there. So you see that he installs it automatically. Okay, so I'm going to remove my Atmel ABR folder and now run again PO run. As you can see, he installed the platform, no? Installing this platform, Atmel ABR 3.2.0 installed, etc. So even if you don't have it available, he will take care of it. Okay? The first time it didn't happen because I already have it. But now, to upload your code, you do the same, PO run, but you define a target. All of this can be found in the help. I think if you do -H, it will tell you the help. No? T is the target, okay? In this case, the target I want to do is upload my code, okay? There's a lot of targets. You can find them in the documentation later if you like, but the clean one, the et cetera, et cetera. The most common one is this. So, boom, no? It's compiled and uploaded. And as you can see here, he's using the same tools ABR do, uploading. First, he does a compilation. He didn't need to compile anything again because the object was already created. He said to you how much RAM and how much flash your code is going to use. That's a nice feature in terms of finding out about RAM, because sometimes RAM is volatile memory. It's the same as in your computer. Your hard drive is the flash, let's say. And your RAM is a memory that when you turn off your computer is erased completely. And every time you load something to see it on screen, to run code inside a software or whatever, you copy stuff to RAM folders and do all the calculations in RAM, but not RAM folders, RAM memory. Okay? We should have a class, I don't know if is there around a little bit of computer architecture.
I think we will have that at the end.
Okay.
Maybe it could be in a code club instead of.
Okay. No, I'm just saying because if some of these concepts aren't clear, sometimes it's more difficult to understand another concept. No?
Would you like to? Oh, but let's decide this now. Would you like to do one on the next code club about computer architecture?
I think just an overview of what are the parts of a normal system and why are they there could be nice. No? I don't know, but
we could. Yesterday class from Guillaume was a little bit oriented into that as well, but probably was too general. Maybe we could go into modern computers and let's say less of tradition, or history, but more into how actually this is built. Okay, and we don't talk about Mac, Linux, and things like this, but we talk about generic concepts. Yeah.
Yeah, buses, communications, CPUs, RAMs, memories, etc. Okay. Well, just to finish this because it's already time to eat. How do you manage libraries? That's one of the best advantages of Platform.io. You don't need to install manually any library unless it is not in the repositories of Platform.io, but almost anything you can think of is there. You have a command called pio-lib, and then you can do, for example, a search, okay? So imagine I want to use which library, strange library you can imagine. Radiohead. No, that's a library for communication between radio RF chips, right? And he will list all the libraries that are related to that. The first one is the clean match. And there's a description of all of the library, what it does, which platforms are compatible with it, etc. And you can find a lot of different libraries. For example, you want to work with servo motors. So you do a pio-lib search servo. And there you have a lot of different libraries, okay? So with this, you can find a lot of libraries. And libraries that you don't find here, you still can use them inside Platform.io if they are available on the internet. For example, using GitHub, libraries that are published in GitHub is very easy, even if they are not available through the library manager. How do we do that? If we go to our Platform.io file, there is all of the things I'm explaining are here in this document of the Fab Academy documentation. You can see here libraries, and in Platform.io init, you just do libdeps, and then you list the libs you want to use, okay? You can list them by name, you can list them by ID. If you find a specific one that maybe the name is confusing or whatever, you can list them by the GitHub address of the library. So he will search on that address and download that library, okay? So for example, I search for the Radiohead library. So I can just put here the Radiohead library, okay? I think that's the only thing I need to do. And now if I do a PO run, I don't know what I did wrong. Maybe I have to include it in the file, yeah. Maybe if I do here and include, it's enough for it to download it. Maybe if it's not included, you don't. Not sure about this, but... Fatal error. I didn't find the proper, I didn't put the proper file name. I'm not sure if maybe it's not uppercase. Dime.
Con comillas, ¿no?
Okay. I think this should be lower, no? Let's see. If I do a PO lib search radio head. No, it is. Well, let's try by ID. Well, no, the program wasn't in platform IO ini. It was here. So you think like this? No. Well, I'm not going to lose time on that, but the normal thing that should happen is he will download the library if you find the proper name and install it and compile it. As an example of how this can be powerful, I'm just going to show you the code that I work normally every day of my life some years ago. The Smart Citizen Kit firmware, that's a little bit complex. We have a code for a couple of chips and stuff, and this is the code for the SAMD chip. And this is the platform IO ini that we use there. No? And as you can see here, I'm going to explain it briefly, there's a lot more settings than the one that we just did today. But this will show you a little bit how powerful it is. No? You can do and automatize a lot of stuff. For example, here, I set up a different platform IO directory to install all the libraries. Why do I do this? Because in that way I can have different versions and different tools than the ones that I have in my system. It's like creating a Python environment, for example. No? You have your specific environment for that project. And that's important when people that uses platform IO for other things wants to compile on a specific project, because sometimes there are cross dependencies and stuff like that. Then build flags, okay? Here I'm telling the compiler that before doing stuff, run this script that I have that does other things, no? Set up some stuff before the compilation process. The platform, normally we use only Atmel SAM platform, like we did before, Atmel AVR, just the name. But here I put an ampersand and the version, the specific version of the platform, because Arduino made some changes on his platform that broke a lot of stuff in my code. So I want to use the previous version, not the latest one. No? Then inside the platform, which packages of the framework Arduino I want to use to specify exactly the version inside the one thing is the platform version and one thing is the framework version. It's a little bit cumbersome, but the thing is you can go as fine as you want to define versions. Board. This board is a Smart Citizen Kit version 2. That's a custom board that we did. So we did our own configuration files that set up not only the chip, the speed of the CPU, etc., but also the pins. These pins are going to be used for UART communication. These pins for whatever, and they are already set up. So maybe you can set up different serial ports already. In Arduino, you normally do a print line and serial begin, no? Serial.begin. But I have a serial ESP because I have a serial that communicates with the ESP. And I have another serial created that I put my own name and I have, etc. No? You can configure almost anything in your chip. framework is the same. We can add extra library folders. And why is that nice? Because, for example, here, this is the code for the SAM chip. And up here, I have the code for the ESP, right? Because I have two chips in the kit. But I have libraries that are shared between both chips. So I can add an extra thing here and have a configuration file that will allow me to do configuration for both of the chips, okay? That kind of things you cannot do in Arduino IDE, obviously, okay? Where I was before here. I was here explaining this, right? Okay. Then this one is pretty nice. Extra scripts. Everyone here loves Python, as far as I can see. You can write Python scripts to do whatever you want in your computer. You can play a sound before upload, after upload. There are defined events around compilation, uploading, etc., where you can do whatever you like in Python. So that's pretty useful. I'm just going to show it here briefly, because you can do stuff. For example, I have a couple of files in GitHub that Platform.io overrides in the framework. For example, a simple bug in the I2C bus that we fixed locally, but we haven't had the time to push to the Arduino repository. So we just clone our own stuff before compiling, even if Platform.io override those with a changed version. No? We can do any kind of things that you like. There is another example that I think is important, is meaningful. In the ESP code, I have a lot more stuff. For example, to uploading the code, since I just have a USB cable for the SAM chip, and that's connected to the other chip, I need to create kind of a bridge mode. So one chip, what it's doing is copying code from one serial port to the other to forward that code to another chip. So I define a command to ask that chip to be in bridge mode. So I have to send that to the chip, so he's able to send the code to the next one. A complex stuff, but what I'm trying to say is I can do that in a couple of lines inside this script, and everything will work. As complex as uploading the firmware through another different chip, through another bus, through et cetera, okay? And to finish, the libdex that I already explained, as you can see here, we use a lot of libraries, right? And all of those are automatically downloaded, updated if you don't fix the version. We normally do this because we use so much, as many libraries that if any of those make changes that break something, people that's trying to use our code cannot compile, and we need to review everything. So we need to fix versions and just update once we have the time to fix the code. No? So you can fix a static version, but you can also go to a GitHub repository, for example, and fix a specific commit. So Platform.io will download the code exactly in the state of that commit to your hard drive and use it to compile your code. So that's kind of the control it gives to you, okay? It gives you a lot of control, but you can still just use it with PyRun-T upload, the one that I did, and it goes really fast compared to Arduino IDE. So I can talk a lot more, but I'm hungry, and I think you are also. I'm very late. Sorry?
Tired.
So try it. I think it's a really nice tool. I have worked with it several years, and it solves a lot of problems. As any tool, it creates another new problems, but in another level. No? Compared to Arduino, if you want to go serious about microcontrollers, I think this is the next step. Okay? And that's it.
So, but let's close it here. Thank you for all the patience. It's a very long session, we know, and it's not meant that you get out of here knowing absolutely everything we just talked about, but try things. We try to, what we decided that we will stay here and do it. So try to iterate a little bit at home, ask us if you need any help, and try to, let's say, work on these things, because it won't happen today, it won't happen in 1 week, it will happen in maybe 6 months or however long it takes to get all these things. I mean, but the sooner you start and the sooner you start playing with these things, the better you're gonna get in a shorter time, and you will be able to use them in serious projects. Okay? And serious projects, for instance, I talk about some assignments at the end and final project as well. Yep. So the idea is that little by little you build on them. And if you don't have any questions or anything, no, so we can go have lunch and enjoy.
Thank you.
Thank you.
Habla un poco más, pero soy muy sordo ya.
Yo también. ¿Has explicado cómo crear una board propia?
No, es un poquito más, o sea, no lo he explicado aquí, he explicado que se puede hacer.
Vale.
No es complejo si tu CPU, si tu chip ya está soportado y no quieres cambiar nada.
Digo, no sé si hará falta, pero utilizo el Arduino. Digo, eso es como Arduino con una LED más. ¿Ya hay algo para utilizarlo, para hacerlo?